All right. Finished my general announcements. I gave students a considerable amount of time to use the equation that we ended on last class in order to complete parts D and E as a warm-up. So looking at part D, you can see in the chart to the right, there is a dog that is 15 weeks old that weighed 44.6 pounds. So if you want to find and interpret the residual, you would start by figuring out, well, how much do we expect this dog to weigh? Now, again, the most common mistake that I see kids making is they ask me, am I supposed to do 34 minus 44, or am I supposed to do 44 minus 34? And my response is always the same. Does this dog actually weigh more or less than what you expected? And the fact that this dog weighs more than what you expected means it better have a positive residual. Okay? So that reveals you should have done the 44.6 minus the 34.172. Okay, and that gets you a positive value of 10.428 pounds. The interpretation of that value is that this dog is 10.428 pounds heavier than expected. Okay, I'm going to go right into part E. People have questions. Now, part E says, given a 20-week-old dog has a negative 7.6-pound residual, what is its true weight? So this is actually asking you to use this equation in an unusual fashion to not find a predicted value, but use a predicted value to find an actual value. In other words, again, your first step would be the same. How much do you expect a 20-week-old dog to weigh? But then you can use that expected value with the residual that was given to you to find the true weight of the dog. So this is actually one of the super rare situations in this class where you don't need non-deterministic language because they told you this dog weighs 7.6 pounds less than expected. So subtract that from the assumed weight and you have what the dog actually weighs. So if you write this dog is expected to weigh 35.192, now you're wrong. Now you're using non-deterministic language when you shouldn't be. You were told this dog weighs 7.6 pounds less than expected. So find the expected weight, subtract 7.6, and you have the true weight of the dog. Question. So the next question, which I did not ask you all to do yet, says a new flat-coated retriever is added to the group for more data. It weighs about 50 pounds, but its age is unknown. A researcher estimates the age of the dog is near 24 weeks, as the model predicts a 24-week-old flat-coated retriever would weigh about 50 pounds. And then they show the work that this researcher used. Would you agree? If yes, briefly explain. If no, give a new prediction for the dog's age. So here's essentially what this person did. They said, all right, we've got this model that says the y-intercept is 8.312 pounds and the slope is 1.724 pounds. And if I go to the table and I scan until I find when would I think you are 50 pounds, I have to scan all the way down to about 24 weeks. That's essentially what this person did. I have a model that predicts you would be about 50 pounds at 24 weeks, so I'm going to assume this dog is 24 weeks old. I have an issue with that because what you're basically doing is you're trying to predict the dog's age, okay? You cannot use a model that uses true age to predict weight. Okay, now a moment ago, what we did was we used a predicted weight in order to back solve for a true weight. Okay, you can do that if you have access to the residual. But if you want to now predict age, you need a whole new equation. Okay, so we know this dog's weight and would like to predict his age, but the model we have predicts weight. So what we need is a different regression model. We have to find a model that is designed to predict age because we know the dog weighs 50 pounds. Okay. Now, by the way, and this is kind of what I alluded to last week, just because 24 weeks leads you to about 50 pounds, when you find the other model, it's not going to be a true inverse. So 50 pounds is not going to lead us to predict 24 weeks. I can guarantee you that. I mentioned it yesterday, one situation where those two equations will be perfect inverses. Somebody say it. If R is 1. If R is 1, then the equations you find, whether you're trying to predict age or you're trying to predict weight, will be perfect inverses. So if one uses 24 and predicts 50, the other will use 50 and predict 24. But here, R is not perfect. In this particular case, we're dealing with an R of 0.88. So it's close. Okay, it's not quite perfect. Okay, it's almost strong. Okay, so let's remember, these are the summary statistics that were given to us yesterday. That's why I put them on the screen. If you want to find this type of model, oh, I forgot to change those to A and B. I knew I was going to miss it somewhere else. So your new formula sheet says this is just called A and this is just called B. Okay, I'll have to fix that later. So what you do is you say, all right, my slope is the R times the standard deviation of the thing I'm trying to predict, which in this case is now age. So 4.9 goes on the top. I use the standard deviation of the thing I'm using to predict, in this case weight, on the bottom. And I get a completely different slope. Okay, notice that is not the same slope of 1.724. It's a completely different slope. Now, this is what I know so far. If I want to predict age, it's going to be some y-intercept plus 0.449 times the weight. I'll zoom in on that so it's easier for you all to see. Okay. 200 seems a little overkill. There we go. Now, if I plug in the average known weight of 29, I know this model better predict the average age of 12 weeks. So if I solve this correctly for the y-intercept, I end up with the following model. Okay. That is the model I should be using to make a prediction. Now I can plug in this dog's weight of 50 and predict age. Now, don't get lost in the process. This is, again, practicing the same process I tried to teach you all yesterday. Using summary statistics, 5 numbers. The mean and standard deviation of the x's, the mean and standard deviation of the y's, and the strength of the correlation between them. Those are the 5 numbers you need. And if you have that, you can get slope, you can find the y-intercept, you can write out the equation. But don't get lost in this question. The question we were being asked was, would you agree? In a word, no, I don't agree. Okay. If yes, explain. Well, I don't need to. I don't need to do that because it's not yes. If no, give a new prediction. So part 2 of this is to use this new equation to predict, okay, I expect this 50-pound dog is probably around 21.429 weeks old. That would be the proper way to make a prediction, not using the wrong model in reverse, as if you're pretending to know the true age when you don't. You're trying to predict age. Okay. So between yesterday and today, we've had a lot of exposure to how do you find a line of best fit. Now what I'm going to try to walk you through, and it's going to be a journey, I'm warning you. It's not going to be easy. But what I'm going to try to teach you is, why is it that if you have a model where 24 weeks predicts 50 pounds, why wouldn't the other model of 50 pounds predict 24 weeks? Like, why isn't this working out? Okay, so I'm going to walk you through a little bit of a journey to end on that punchline. Go ahead and turn the page. The admissions office at Mythical College State University is interested in updating their incoming freshman standards. Data on SAT scores and GPA of this year's incoming freshman class have been collected, and a weak positive linear correlation between SAT score and GPA was not surprisingly found. Summary statistics have been provided. So you have the average SAT score with the standard deviation. This is obviously from a time when there were 3 sections on the AP, on the SAT. I know that we've dropped back to 2, so it's on a scale of 1600, but this is data from when it was out of 2400. So the average SAT, standard deviation, average GPA, standard deviation, and correlation. Now let's go back a moment. If these distributions truly are normally distributed, remember that there are some foundational ways of using those 2 numbers. Okay, 1837 and 178. If I do 1837 minus 2 times 178, and I do 1837 plus 2 times 178, this is again based on the assumption the distribution of scores are normal, then anything outside of that range would be considered unusual for an incoming freshman at this college. Anything lower than 1481, anything higher than 2193. That's what a normal curve would suggest. Not that it has anything to do with what we're talking about right now, but just want to remind us, we can't forget the basics. Okay? Now, go down. Part A says, if an incoming freshman's SAT places him at the 90th percentile, so you are beating 90% of people, okay, what SAT did he get? Round to the nearest 10. Now, by the way, I can logically deduce why I should have shaded about that much of the picture. Let's see if you all remember this. What percent is that? 68. What percent is this? 50. What percent is that? 84. Everybody got that? Okay, the last little piece that I just did, this is half of 68, which is 34, plus 50 is 84. So if I shaded from this point down, that would be 84%. But this person's at the 90th percentile. So they're obviously a little bit further up than that. Does that make sense? What command, by the way, do I use to actually know that true z-score? Inverse norm. If you don't know the z-score, you can't use normal CDF. Okay, if you're looking for the z-score, you use inverse norm. So I would say, all right, this person to be beating 90% of other kids has to be 1.282 standard deviations above expected. Okay. Now, if you want to set up a z-score formula, if that's what makes sense to you to figure out what was this person's score, more power to you. I have no problem with that. Personally, I'd rather just do it more straightforwardly. I'd rather just start at the center, 1837, and add 1.282 times the standard deviation of 178. That to me is what makes more sense. But if the green makes more sense to you, go for it. Either way, you're going to end up with the same thing. When you round it to the nearest multiple of 10, as you were asked to, it was 2070. Okay? All right. Now, an admissions officer states his SAT is at the 90th percentile, so his GPA would probably also be at the 90th percentile. This is what this person is thinking. Okay? Under what conditions would this be a statistically justified statement? Perfect correlation. That is the only way this would make sense. If you're at the 90th percentile for one, the only way I'm going to predict that you're at the exact same location for the other is if the correlation was perfect. Now, don't get me wrong. There is a positive relationship. These are variables that apparently move together. So if you have somebody who is above average in SAT, it makes sense to predict they'd be above average in GPA. But the question is how much above? Okay, that's going to depend on the strength of the correlation. And you're only going to go equally as far. Hey, don't do that. You're only going to go equally as far if the correlation between the two is 1. Okay? So I'm going to constantly go back and back and back and back to kind of keep us all organized. Part A is you got somebody at the 90th percentile. What'd they get? 2070. Part B is, okay, here's a false way of thinking about how to use this knowledge to predict the GPA. Okay, turn the page. We're now going to do it in a correct way. Part C is, in Part A, you should have found the 90th percentile in the SAT led to expect the student to get a 2070. Now use this to predict the student's GPA. So I need a model that uses a known SAT score because we were told they're at the 90th percentile. We were able to find out, okay, that means they got a 2070. So we need a model that uses a known SAT score to predict GPA. So this, I knew it was going to be again. I knew if I forgot to retype it before, I would have forgotten to retype it here. Okay? So this is what we need. So we start with this. The correlation times the standard deviation of the thing you're trying to predict. In this case, we're trying to predict GPA. So it's the standard deviation of GPA that goes on top. Standard deviation of SAT that goes on the bottom, because that's the thing we're using to make a prediction. We end up with the following slope. I now know, just based on that number, let me zoom in on this for you all. Okay, based on that work so far, this is what I know. That if I want to predict GPA, it's some y-intercept plus that slope times the SAT. I also know that if I plug in the average SAT score and I plug in the average GPA, because the mean point has to be on the line of best fit, that will allow me to solve for the y-intercept. So I multiply those values, subtract from the other side, and I end up with my y-intercept. And now I know the following, that if I want to predict GPA, I have my slope, I have my y-intercept. And in this particular case, all I'm going to do is plug in 2070, multiply by the slope, add the y-intercept, and boom, I've got my predicted GPA. Okay. So again, at the risk of being overly redundant, okay, Part A was somebody's at the 90th percentile. What was their score? 2070. Part B is, okay, well, then what should their GPA be? And somebody falsely says, well, then they'd also be at the 90th percentile. No, I don't agree with that. Okay, fine. What do you think it's going to be? I think it's going to be 3.24. Now, part D comes along and says, all right, well, based on that GPA that you just calculated, okay, let me zoom out so we can see this a little more clearly. Based on the expected GPA, percentile would you place this student? So you have a normal curve. This person got a 3.247, which you can see on this curve that I've drawn is somewhere between 0 and 1 standard deviations above expected. So it's, 50 plus some percentage, not quite as high as 84. Okay. So we would know, where is this score? That's the first thing we need to calculate. How unusual is a score, a GPA of 3.247, when you expect, that's the average, a 3.01, and the standard deviation is 0.32? You find out this person is 0.742 standard deviations above expected. So how do I find the area under that curve up to 0.742? What command do I use? Normal CDF. Or if you're more comfortable with the pink Z chart, fine, go for that. Okay. But if you start at negative 99 and go up to that Z-score, you find out I should expect the student to be at roughly the 77th percentile. Okay. Now, in a moment, I'm going to summarize everything we just did at parts A through D in one simple step. Okay. And I can actually demonstrate all of that math in about 4 lines or less in your graphing calculator. Let me think. 1, 2, in 3 lines. 3 lines. I could summarize everything we've just done with 3 commands in the calculator. Okay. So here's the idea. Notice, by the way, this person was not expected to be the same distance above expected. Okay. We were told this person has an SAT that places them at the 90th percentile, 1.282. And the only way you're going to predict that they're exactly 1.282 above in GPA is if the correlation is perfect. Okay. But in the end, they are positively related. So if you're above average in SAT, we should be predicting you're above average in GPA because you have 2 variables that travel together. If one is above expected, the other is expected to be above. Okay. But not 1.282 above. In this case, only 0.742 above, apparently. Okay. So the question is, how do you get these values? Why is it that if you're at the 90th percentile in SAT, I'm predicting you're only at the 77th percentile for GPA? Both are still above average, by the way. Okay. So the driving concept is that given correlation between 2 variables X and Y, if an X value is Z standard deviations from average, we expect the corresponding Y value to be RZ standard deviations from average. Okay. This is a really fancy way of saying we expect the slope be SY over SX. But you're only, if you go over 1 standard deviation in X, you only expect to go 1 standard deviation Y if the correlation is perfect. But if the correlation is, say, 0.5, let's say it's weak, well, then if you find somebody who is, say, 2 standard deviations above expected in X, you shouldn't be expecting them to be 2 standard deviations above in Y. You're only willing to go half that distance because the strength of the correlation is 0.5. You'll notice the slope formula on your formula sheet is literally, for every 1 SX you go over, we expect you to go 1 SY over, up, except for the fact that you have to multiply that by R. Okay. Now, if R is 1, fine, it's SY over SX. Now, here's the sort of mathematical way of talking about this. Based on the driving concept, write a mathematical equation to demonstrate the relationship which links the correlation and the Z-scores for this student. Well, the bottom line is, here's how you could do this all at once in your calculator. I'm going to demonstrate this in a moment. I'm going to type it out. If you are told you're at the 90th percentile, you can use the command inverse norm 0.90 to figure out your Z-score. And then you can say, all right, well, if you're 1.282 standard deviations above in SAT, I'm only going to expect your 1.282 above in GPA if the correlation is perfect. But it's not perfect, so I'm not going to go that full distance. I'm going to multiply that number by R to get the predicted Z-score. That's as simple as this becomes. And then you can, so right there, just notice, I just jumped from part A to the end of part D. I got, okay, you're at the 90th percentile. Well, then this is what I expect you to be at with the other variable, because this is the strength of the correlation between them. And then I could just do normal CDF to figure out the percentile. This whole process, part A through D, could literally be replaced by 3 simple lines in your calculator. Okay, 90th percentile, where are you on the curve? Let me multiply by that by the correlation to figure out where I expect you to be on the other curve. and let me convert that to a percentile. This is absolutely a process I will expect you all to be able to handle on next week's test. I give you two variables. I say the correlation between them is 0.74. And then I tell you, well, this person has this score, and you figure out that's like 2.4 standard deviations above expected. And I say, what do you think their other score is going to be? And I'm not going to give you the summary statistics. I'm not going to give you the linear model. You're not going to have access to all the information you need. I'm simply going to tell you, okay, you're 2.4 standard deviations in one, and the correlation between them is 0.74. What do you expect their other score to be? And you can tell me, I expect them to be 1.776 standard deviations above expected. It's that simple. Okay. R is literally a measure of, for every one standard deviation X you go, how many standard deviations in Y do you expect? And it could be positive or it could be negative depending on the correlation. Okay. Now, in case this isn't firmly sticking, because I know this was kind of a lot to dump on you, I want to show you another example. Okay. Turn the page. And what I told you before is that part F is kind of like parts A through D mashed into one problem. And then part G is kind of like part E, the punchline all over again, just so you can see another example of what's going on. Okay. We're almost done. I promise. Okay. We only got about 10 minutes left anyway. Another student has a GPA of 3.85. Notice they're giving you GPA now. They're not giving you SAT. So the old formula we had is trash. Can't use it. Okay. Predict this student's SAT using a regression model. This time, do not round your prediction at all. Okay. So I tell you, let me zoom in on this, and that way I can change all my little notation. I'll update this for the notes, by the way. I figured I'd miss where this needed to be updated in random spots. So we need a model that uses GPA to predict SAT. So this is the formula for slope. Okay, I use the standard deviation of SAT is now on the top because that's the thing I'm trying to predict. I end up with a completely different slope, 317. By the way, in context, what that basically means is if your GPA goes up by 1, I expect your SAT score to jump by 317 points. I then am here. And I know that if I plug in the average GPA, the equation should lead me to predict the average SAT. That's how I'm able to solve for the y-intercept. So I have this model, and I was told we're dealing with a student that has a GPA of 3.85. So I plug 3.85, and I get my predicted SAT of 2,130.33. I guess I could have rounded that to the third decimal. But the directions were do not round your prediction at all. So I wanted to keep all 4 decimals. Okay. So this is one way you can make a prediction. If you have all 5 summary statistics, then you can use those 5 numbers to find a model and then plug in a number and make a prediction. Fine, no problem. Or we could do it a completely different way. So this is part G that I'm getting to now. This is sort of the punchline way of getting to it. Confirm your prediction in part F using z-scores and correlation. So here's the other way you could have gotten to this exact same prediction. You could have said, all right, you've got a GPA of 3.85. Okay. Where is that on the curve? So find the z-score for GPA. Now, if you have a z-score, if you are 2.625 standard deviations above in GPA, I'm only going to predict you are that exact same amount above expected if the correlation was perfect. But it's not perfect. So what I do is I take that z-score and I multiply it by the correlation. And I say, okay, if you have a z-score of 2.625 for GPA, I am willing to predict 0.57 of that for SAT. And so I'm willing to predict, if you're above average in one, I'm willing to predict you're above average in the other because the relationship is positive. They travel together. But I'm not going to go that far out on a limb. I'm not going the whole distance because the correlation is not perfect. I'll go 1.49 out. Okay. Now what I have to do is figure out, well, what SAT score is that? So again, if you want to set up a z-score formula and solve for X, more power to you. My personal preference is to start at the average SAT score. of 1837 and just add 1.49625 standard deviations to it. And lo and behold, you get the exact same number we got in the previous part. This is the punchline, okay, to see that there are two completely different ways of making predictions in linear models. You can use the linear model, or you can simply use the relationship of the z-scores, which is what R is. R is literally the slope between z-scores. Now, here's the good news. There's no more mathematics to do. It's just sort of thought process stuff. And I have a visual to sort of explain what I was trying to get you to understand. And again, this is all about why is it called regression, specifically regression towards the means. To me, this is like a super fascinating thing if you can wrap your head around it. Okay. Last thing of the day, we're going to play quote unquote ping pong to understand regression. Use the starting GPA of 3.85. So let me first explain this visual, because if you don't understand the visual, you're not going to understand any of this. The average GPA is 3.1. If you are one standard deviation above expected, then you have a GPA of 3.33, so you have a z-score of 1. If you are two standard deviations above expected, that's a GPA of 3.65, your z-score is 2. Everybody got this? I'm just trying to make sure we know how to read this visual diagram. Okay. So if you have a GPA of 3.85, that would put you right about here at a z-score of 2.625. Now, the only way I'm going to predict that you are equally far above in SAT is if the correlation between them is 1. If the correlation was 1, then I'm going to say, all right, if you're that far above average in GPA, I'm going to predict you're exactly that far above in SAT. Everybody got me? But that's not what's happening here. You don't have a positive correlation. So what I'm going to say is I'm going to drop this out completely because the correlation isn't positive. And what I'm going to say is, okay, if you are above average in GPA, because these variables are positively related, I do expect you to be above average in SAT. But the degree to which I'm willing to go out on that limb is solely based on the strength of the correlation. So what I do is I multiply this z-score by 0.57. I multiply it by the correlation. I say, okay, if you have a GPA of 3.85, I am willing to predict you have an SAT of 2103 because that is 1.496 standard deviations above expected. We're going to do this a couple times. Now, let's just be clear, if one equation uses 3.85 to predict 2100, I kept saying it over and over again, that does not mean the other equation will use 2100 to predict 3.85. Everybody got me? That would make no sense. The reason for that is, let's flip the script a little bit. Let's pretend this is somebody's actual SAT. Let's say we find a student that has an SAT of 2100. So they're 1.49 standard deviations above expected. Well, I'm going to say the only way I would predict you are equally far above in GPA is if the correlation were 1. Everybody got it? Because if you're above average in SAT, I'll predict you're above average in GPA, but I'm not going the full distance unless the correlation is perfect. So what do? I ask myself one simple question. How strong is the relationship between these variables? So what I do is I say, oh, so you got a 2100? You are 1.49 above expected in SAT? Well, then let me multiply that by 0.57. And that's going to lead me to predict a GPA that is 3.2 standard deviations above expected, or excuse me, 0.852 standard deviations above expected. Do you get why I called this ping pong? We're just going to bounce from side to side to side. Now, let me be clear. If the correlation was 1, then if you are this far above in GPA, I will predict you are exactly that same above in SAT. And if you're that far above in SAT, I will predict you're exactly that far above in GPA. And we'll just sit here and ping pong, ping pong, ping pong in the exact same location if the correlation is perfect. Got it? Correlation isn't perfect. So every time you make a prediction, you have to multiply by R. So if you have a GPA that places you 0.85 above expected, then I'm going to predict your SAT is only 0.48 above expected. And if you have, it keeps going, folks. I'm not going to stop. If you have an SAT that's 0.486 above expected, I will predict, as soon as I learn how to click, that you have a GPA that is 0.27 above expected. And if I find a student that is 0.27 above expected, I will predict, as soon as I learn how to click, that that student is 0.157 above expected. Now notice, if we kept going and going and going and going, and we kept multiplying by 0.57, 0.57, 0.57, what's happening to the z-scores? It's approaching zero. The z-scores keep getting smaller. We go from 2.6 to 1.4 to 0.8 to 0.4 to 0.27 to 0.15. Every time we make a prediction, what we say is, if you're this far above expected, I'm not going to predict the same amount above expected. I'll go a certain amount of that based on the strength of the correlation. So every time you make a prediction, you're getting closer and closer and closer to a z-score of 0. On a normal curve, what has a z-score of 0? The mean. So every time you make a prediction, you are regressing towards the mean. That's why it's called linear regression. Because if you plug a known value in and you predict a value, the predicted value will always be relatively closer to its mean than the value you started with to make the prediction, unless the correlation is perfect, in which case they'll be equidistant from the relative means. And by the way, let's just pretend for a moment the z-score was like 0.99, like a really strong correlation. Well, then if you're this far above, I'm going to basically predict you're that same amount, basically predict you're that same amount, basically predict you're that same amount. We would have to ping pong back and forth, back and forth, back and forth, back and forth, back and forth way more times if the correlation was 0.99. Does that make sense? Like it would take us a really long time to regress towards the mean, but we would eventually get there. Okay. All right. I'm done. Hopefully I didn't melt your brains too much. I tried to be as organized as I could. I provided a couple other pictures to show what would happen if you start with a negative z-score, as well as if you're working with a negative correlation. That one's a bear. That one's annoying to try to figure out. So if you can figure that one out, more power to you. Okay. I find it interesting. But at this point, I would say try 3.212 on your own time at some point. Okay. But next class, we're going to start with 3.213. All right. For those watching the video, I will not reveal the answer key to 3.212, but it will be posted on Canvas Notes. Thanks for watching. Have a good one.